Welcome to Blueprint to Reality. Today, we're exploring an incredible engineering feat: how earthquake-proof buildings can bounce back from destruction. Earthquakes can cause severe damage, but advancements in building technology are helping structures recover and even survive intact. Let's dive into how this is possible. The basics of earthquake-proof design. First, let's understand what makes a building earthquake-proof. Earthquake-resistant buildings are designed to withstand seismic forces through a combination of smart engineering and advanced materials. Key features include flexible foundations, which allow buildings to absorb and dissipate seismic energy. Instead of collapsing, these structures are designed to sway and shift without losing their integrity. They also incorporate dampers, devices that absorb shock and reduce vibrations. Think of them like shock absorbers in a car, but for buildings. Advanced technologies for recovery. But being earthquake-proof is only part of the story. To truly bounce back, buildings must be able to recover from damage and remain functional. Here are some cutting-edge technologies that help buildings recover after an earthquake. 1. Base isolators. These are large, flexible bearings placed between a building's foundation and its superstructure. They allow the building to move independently of the ground motion, reducing the amount of stress transferred to the structure. 2. Self-healing materials. These innovative materials can repair themselves after sustaining damage. For example, self-healing concrete contains special capsules that release healing agents when cracks form, helping to restore the concrete's strength and durability. 3. Post-earthquake reinforcement. Some buildings are equipped with systems that allow for rapid assessment and reinforcement after an earthquake. These systems can detect damage and automatically deploy additional supports or reinforcements to ensure the building remains safe and functional. Real-world applications and examples. Real-world applications of these technologies are already making a difference. In Japan, a country with high seismic activity, many buildings are designed with base isolators and advanced damping systems. The Tokyo Skytree, for example, is equipped with a massive damping system that helps it sway safely during an earthquake. Similarly, buildings in California, a region prone to earthquakes, are being constructed with self-healing materials and other advanced technologies. These innovations not only protect lives but also minimize disruption to businesses and communities after a quake. The future of earthquake resilience. The future of earthquake resilience is promising. Ongoing research is focused on developing even more advanced materials and technologies to enhance building recovery. Innovations like shape memory alloys, which can return to their original shape after deformation, and more effective early warning systems are on the horizon. As we continue to improve earthquake-resistant technologies, we're moving closer to a future where buildings can not only withstand but also quickly bounce back from the impact of earthquakes, making our cities safer and more resilient. So there you have it. Earthquake-proof buildings are not just about surviving the quake, but about bouncing back stronger than ever. Thanks for tuning in. If you found this video insightful, be sure to like, share, and subscribe to Blueprint to Reality for more engineering breakthroughs.
See you next time.
Welcome back to Blueprint to Reality. Today, we're going to break down the key differences between two popular slab systems in building construction: flat slabs and two-way slabs. Both systems have their strengths and weaknesses, but which one is right for your project? Let's find out. First, let's talk about structural design. In a flat slab system, the slab is directly supported by columns, without the use of beams. This allows for a simpler and cleaner ceiling design. However, since there are no beams, flat slabs rely on thicker concrete and larger column heads, or drop panels, to distribute loads effectively. On the other hand, two-way slab systems use beams that connect columns, and the slab rests on these beams. The load is transferred in two directions, both along the length and the width of the slab. The presence of beams means the slab itself can be thinner, but the ceiling design may be less aesthetically flexible due to the beam projections. Next is how each system handles load distribution. In a flat slab, the load from the slab is transferred directly to the columns. Because of this direct load transfer, flat slabs need to be thicker or require the addition of column capitals to prevent punching shear failures, especially in areas with high loads. This can lead to increased material usage. In a two-way slab system, the load is transferred across beams in both directions, which distributes the load more evenly. This leads to a more efficient design for handling heavier loads, especially in multi-story buildings or structures with a grid-like layout. Now, let's talk about design flexibility and space utilization. One of the main advantages of the flat slab is the freedom it offers for open spaces. Without beams, you have more design flexibility for architectural layouts, especially for offices, malls, or parking garages. You can create large, open rooms without the visual or spatial interruption of beams. In contrast, two-way slabs require beams, which can limit interior space design. Beams create drops in ceiling height and may affect the positioning of utilities, lighting, and partitions. However, the added strength of this system can allow for thinner slabs and a potentially lighter structure overall, which is beneficial in smaller-scale projects or residential buildings. Cost and construction time are always important considerations. Flat slabs are generally quicker to construct because of their simpler formwork. The absence of beams means fewer steps during construction, which can reduce labor costs and save time. But remember, the thicker slabs and additional reinforcement may increase the cost of materials. Two-way slabs, on the other hand, involve more formwork and reinforcement due to the inclusion of beams, which can slow down construction and increase labor costs. However, the overall material cost may be lower, especially if the beams allow for thinner slabs. So, when deciding between flat slab and two-way slab systems, it comes down to your project's needs. Flat slabs offer more open space and speed, while two-way slabs give you more strength and cost efficiency in certain designs. Thanks for watching. If you enjoyed this breakdown, hit like and subscribe for more civil engineering insights, only on Blueprint to Reality. See you next time. Hello everyone and welcome back to our channel. Today, we're diving into an exciting topic in civil and structural engineering, how advanced simulation tools are revolutionizing the field of structural analysis. These tools are not just changing the way we design structures. They're enhancing safety, efficiency, and innovation in ways we couldn't have imagined just a few decades ago. 1. The importance of structural analysis. First, let's briefly discuss why structural analysis is crucial. When engineers design buildings, bridges, or any structure, they must ensure that it can withstand various forces and loads, such as gravity, wind, and seismic activity. Traditional methods of structural analysis often involve simplified calculations and assumptions, which can sometimes lead to suboptimal designs or, worse, structural failures. This is where advanced simulation tools come into play. 2. What are advanced simulation tools? So, what exactly are advanced simulation tools? These tools include software programs that use finite element analysis, computational fluid dynamics, and other numerical methods to create detailed models of structures. By simulating real-world conditions, these tools allow engineers to visualize how a structure will respond to different forces throughout its life cycle. For example, finite element analysis software breaks down a structure into smaller, manageable elements, calculating how each one behaves under various conditions. This level of detail provides insights that traditional methods simply cannot offer. 3. Benefits of advanced simulation. Now, let's talk about the benefits of using these advanced simulation tools in structural analysis. 1. Enhanced accuracy. One of the primary advantages is enhanced accuracy. By taking into account the unique material properties, boundary conditions, and load scenarios, engineers can make better informed decisions. This leads to designs that are not only safer, but also more efficient in material usage. 2. Cost efficiency. Next is cost efficiency. Although there may be an initial investment in software and training, the long-term savings are significant. With accurate simulations, the need for costly physical prototypes and extensive testing is reduced. Engineers can optimize designs and identify potential issues early in the process, saving both time and money. 3. Improved safety. Moreover, safety is a critical concern in engineering. Advanced simulation tools enable engineers to conduct comprehensive risk assessments and safety evaluations. By simulating extreme conditions, such as earthquakes or heavy winds, engineers can better understand how structures will behave and implement necessary reinforcements or changes before construction begins. 4. Real-world applications. Let's look at some real-world applications. For instance, in the aerospace industry, companies use advanced simulation tools to analyze the structural integrity of aircraft components under various flight conditions. In civil engineering, simulations help design earthquake-resistant buildings in seismic zones, ensuring they can withstand potential disasters. In conclusion, advanced simulation tools are a game-changer in structural analysis. They provide engineers with the ability to create safer, more efficient, and cost-effective designs. As technology continues to evolve, we can expect even more innovative solutions that push the boundaries of what's possible in engineering. Thank you for joining us today. If you found this discussion insightful, please like, share, and subscribe for more content on engineering topics. Until next time, keep innovating and pushing the limits of design.